Welcome to another episode of our interviews with authors. Today we're doing a longer format interview to learn more about the career and experiences of an established author, editor, and prominent member of the crystallographic community, John Helliwell. John, it is a great pleasure welcoming you to Interviews with Authors.
Well, thank you very much for inviting me, and truly it's an honor, and I've been really very pleased with being able to be an author within the Acta Cryst family.
We've got a number of interviewers today. Joining us today in the interviewing panel, we have Professor Cryst from Sao Paulo in Brazil. Christy?
Very nice to be here again.
We also have Mark Van Reyk from Madrid in Spain. Mark?
Thank you, and welcome from Madrid.
And finally, our commissioning editor, Roberto Steiner, is also joining us from either London or Padua in Italy. Which one is it, Roberto?
Well, hello, everyone. Actually, I'm in Malta right now, but but yeah, I'm both Padua and London, but at the moment in Malta.
John, you're in York.
I am, yes. Sorry. I failed to
my alma mater, having done physics undergraduate degree 1971 to 74, and of course I was on the staff for several years as well in the physics department in the mid 1980s. So anyway, yeah, wonderful place, York. So you're very lucky to be employed there.
Indeed, it's a fantastic place to be, and very welcoming environment and lots of knowledgeable people here. Let's get started with the interview questions. Roberto?
Yeah, very pleased to ask the first one. I'm also, by the way, a York alumni. I did my postdoc there, so there's a connection there as well. John, so first question from me. So what inspired you in pursuing a career in X-ray crystallography and in structural biology, really?
Well, again, mentioning York, it goes back to my undergraduate physics degree, and the final year, the third year as it was at the time, the Bachelor of Science, Peter Main did an option course, and it was on biophysics, and it really inspired me. And then specifically within that, I do recall vividly the protein crystallography and Peter Main explaining the Max Perutz hemoglobin story. And Max Perutz had published a New Scientist, a vividly entitled popular article on hemoglobin, the molecular lung. And it was the binding of oxygen, obviously, and the analogy therefore, but at the molecular level with the lung, I thought was fabulous. And then the fact that physics, X-ray crystallography in particular, could give such an insight, I just thought was absolutely amazing. And then I was also very much privileged to have X-ray crystallography lectures from Michael Wolfson, who was also in the physics department. He was professor of theoretical physics. So I had this very rich, fertile soil, I suppose we would call it, that set me running. And I looked up in the graduate opportunities at the Career Centre for PhDs, and that led me to find out about the Laboratory of Molecular Biophysics in Oxford, and decided to apply there and got in. So that really was another fabulous stroke of luck. And I picked a great project with Margaret Adams there. David Phillips interviewed me, which was a fairly daunting experience because he had this sort of very piercing, penetrating, inquiring look and the mind to go with it. But yeah, I had a great project with Margaret. And in fact, that enzyme that was my work, of course, I did a topical review. I invited Margaret, first of all. She said, "Oh no, I've stopped thinking about proteins." And because she'd retired some 10 15 years before, and she suggested Stefania Hanau, and in Italy there, and she had worked with Mario Ripper, who was a biochemist who specialized in that particular enzyme, 6-phosphogluconate dehydrogenase. And so together we wrote that topical review on 6-PGDH. And that actually takes me, I don't want to answer too lengthily, but it does take me to the origins of Acta F, which was in my period as editor-in-chief. And there were very much on the up with structural genomics. And Acta F was very much a complement to Acta Cryst D, which was not only biological crystallography methods, but also structures. But the pace of structures arriving into the PDB was such that it seemed to us, and Ted Baker was president of the International Union of Crystallography at the time, that it would be good to have a more communications, to take the fast stream of new structures. And there was a lot of industry participation in producing structures, and they could be perhaps persuaded to publish many of their ligand protein structures, not necessarily all of them, obviously. With crystallization as a third category, popular at the time, that really, was how Acta Cryst F was approved by the IUCR Finance Committee. So Howard Einspar and Mitchell Guss, of course, were the founding editors and were the main people that did the heavy lifting with respect to.
So John, going back to the original question, so we can say that it was those inspiring lectures when you were an undergrad.
Yeah, absolutely, and very, very clear lecturers.
Yeah,
and very accomplished researchers, of course,
sure.
Which will connect in with one of the later questions about how, in the modern university world, can we actually shoulder the work of researcher and teacher.
Thank you, John.
Yeah, I remember the book of Wolfson, starting several times during my thesis and postdoc, getting a little bit further each time.
Yeah, beautiful book.
Beautiful book.
And Michael made a second edition, which is kept it nicely up to date.
I don't think I ever completely finished it. Never mind. So you've obviously had a very successful career, and what were the key challenges and how did you overcome those?
Well, it's always relative, it's a bit like playing squash. There's always somebody much better than oneself, and all you can do is do your best. And as my mother used to say, I mean, the biggest challenge, I think the same for all of us, is that transition from, the postdoc period where you're on a sort of probably 3-year at best appointment cycle. And it's a very tough period because by then, people getting married and that sort of thing. And so you've got other wider commitments. It's very, very hard at sort of that stage of the career. So the transition to a permanent role and permanently funded role is I think probably the biggest challenge. And I didn't make it in one leap. I mean, I got a 5-year opportunity jointly with the synchrotron, the new synchrotron source at Daresbury in the northwest of England. And that was jointly with Keele University Physics. So that was my big chance, and I either made something of that or not, and if not, it would be the end somehow, and I would have to pick something else. But I did make a success of it, yeah, so that was really the big break.
Yeah, I think that resonates with young people now.
Yeah, but I mean, in an academic or research career, I think it's challenges in all sorts of ways, with respect to, performance metrics, as it's an increasingly managerialistic that universities monitor, how well you're doing with research funding. And, if you have a bit of a dry period, you notice things happen to you, like be given extra jobs to do, that you end up in that, if you're not careful, into that negative spiral, because all your time is going into these other jobs that you've been given.
Our next question is about juggling. How does one balance research with teaching responsibilities, or is this like a two-person job?
Well, I think it's absolutely vital that we try, and that universities in particular that aspire to be the best should do that, because I think the way in which in our teaching, obviously particularly in the final year, but also in earlier years of the undergraduate degrees, people are eager. If you're in a sort of good intake, let's not beat about the bush, with excellent students, then they're eager from day one, and they want to hear about the latest stuff as well as the foundation stuff. And so you've got to try as individuals, and the institution has to find ways to help and facilitate your efforts to be both. But of course that transforms into an issue of work-life balance, because if you're not careful, then you basically working all the time, and that is not good for yourself or for family, or indeed in the end back to the institution. If you're sort of fragile because of too much work, then in the end you could be not good to the institution either. So it's very difficult in the end, if you want to do the perfect job or be the perfect person at the job. It's a difficult balance. I think so much in life is a lot of balance, really.
So we can conclude that this is a three-person job.
Well, I mean, I also worked a lot of the time in Daresbury, and the scientific civil service did compulsory training. In universities do voluntary training, and largely I'd sort of always said, oh, I was too busy for doing these skills training things. But the scientific civil service at Daresbury, they force you to do them, and they prove to be extremely valuable, these different skills that training courses you went on, presentation or negotiation, risk analysis, that sort of thing. And there are economies that you can make with how you manage your time, and so productivity goes up through what were in the end fairly small time investments to go on these sort of training events.
Indeed.
I think it's my turn. And before I ask my question, John, I have to say I'm very happy to be here with you. It reminds me my beautiful time in Manchester during my PhD. So I feel like I'm talking to my a scientific uncle. So very happy to be here with you. My question, well, being your lab, an international lab, and I remember that. My question is, how important do you think international collaborations have been in your research projects?
Yeah, well, it's great to be meeting up with you in this format. I mean, obviously, the scientific uncle bit for the others is just to say, well, of course, you were working with Bill Hunter, my colleague, a really marvelous colleague, and Bill in the end went to Dundee University, which was sad for me, and that he'd gone. But anyway, he did very well up there. And of course, you were with him, and it was great to have you in the lab, and Bill was jointly energetically forging this new lab in Manchester. So international collaborations, the most important one, they've always been there, but also national collaborations. But the most important one probably was the European Synchrotron Radiation Project, ESRP, which initially was based at Geneva at CERN. And then out of all of these international contacts, people coming together from the different European facilities and even more widely around the world. The ESRF was funded as a facility, and was the first of the third generation synchrotrons, and they asked me to lead the discussions of the working group for macromolecular crystallography, and I wrote the chapters for MX in the foundation phase report. And we didn't get everything right. I mean, particularly the expansion that happened. Well, I suppose in a way we did anticipate it, but we would never have secured the resource for the number of beamlines that had happened eventually at the ESRF. So our bid was perhaps too modest in the foundation phase report. But then in terms of protein crystallography and structure collaborations, you know, the Imperial College London has been a very strong collaboration for me with Professor Naomi Cheyenne, and you know, internationally, particularly with the US, I suppose, not so much with Asia and Japan in particular, but obviously another very strong place. I did chair committees in Japan, and within that were very much collaborative moments in as advisory, you know, committee input to big projects there. You know, so, and I mean, perhaps most fundamental of all, of course, is the International Union of Crystallography, you know, which is a fabulous opportunity for collaboration with experts and colleagues around the world. You know, so the Commission on Synchrotron Radiation, which Philip Coppens, who was president at the time, was very keen on, and so I established that commission through the invitation of Philip Coppens, who was State University of New York in Buffalo. Anyway, just that was just a few examples of how you know, research is very much a community effort, really.
Thank you, John.
I think it's my turn again now, John. So you've obviously had a very successful career, but can you tell us a little bit about stuff that you would maybe do differently, or stuff that didn't work?
Yeah, well, the painful one to mention, of course, is how I got angry with the chief executive at the CCLRC, the Council for the Central Laboratories of the Research Council. And I won't go into the gory details, but I didn't handle that well, and resigned in anger. And that was not a good period of time. So I mean, I mentioned all these training courses that I did, and of course the only one that was missing was the anger management. But anyway, one learns from life as well as courses, so yeah, much better at
scientifically, maybe something that you would have liked maybe to pursue in hindsight, or?
Well, I mean, in terms of challenges that never come off somehow, you know, you do have pet themes that you would like to see develop.
Yeah.
And in research, and you know, they're just fishermen's stories, aren't they? They're the big fish that you never manage to land on the bank. But I mean, a good example of one where landing the fish on the bank was a long time coming, but it did happen eventually, is this story of the protein crystallography at body temperature. So back in York, in the physics department, when I was on the staff in the mid-80s, I had a student, and we were heating up a protein crystal using a hairdryer and measuring the temperature at the crystal best we could with a thermocouple. And we got up to about 55 degrees when the diffraction had disappeared, and then we cooled down, it came back. And that left a lasting memory and a sort of a simmering wish to do that experiment better. We never published it. And then just last week, we managed to with my collaborator and her student, Dr. Alice Brink, and her student, Francois Jacobs, in South Africa. There, we managed to publish an actual study with one of the rhenium models for technetium compounds, and it's very much a chemistry-oriented focus with respect to what the bound rhenium compounds did at the higher temperatures. So basically the covalent ones remained and the non-covalent ones sort of drifted off into the solvent channels. And you know, so for non-covalent ligand binding, body temperature protein crystallography could perhaps be really rather important. Anyway, so that's a story of a fish that was a long time in the catching, but finally did land on the bank of the river.
Thank you, John.
John, it's me again. You have a very inspiring career. What advice would you give to young scientists starting in crystallography today, given the rapidly evolving landscape?
And it is a very rapidly evolving landscape. You know, the Nobel Prize with the artificial intelligence, machine learning for protein design and protein prediction, protein fold prediction, tells us that. But of course, also for all those things that we struggled to crystallize and never quite managed it, cryo-EM for those big complexes has happened. You know, I think the principal advice is to embrace them all. But you know, that it's obvious that they all have their own domains of application. So, you know, cryo-EM, you know, cannot deliver precise structures below a certain molecular weight, say 100 kilodaltons or 80 kilodaltons. And any design or prediction precisely that, you know, that you don't know that they're right until you actually do an experiment. And you know, protein crystallography or cryo-EM, you know, are there for doing that. And of course, the NMR in solution is obviously something I've also, well, not obviously, but something I've also admired. And sort of, I even taught an undergraduate physics course on NMR. But it's actually in the end hard to master properly the skills for each one of these, you know, which are very sophisticated methods. And so you are bound, I feel so anyway, by, you know, the sort of the particular skill set that I have, you know, hard won, you know, through decades, you know, with protein crystallography. And I've done some microscopy, not cryo-EM. We tried to get funding for it, but failed. But electron microscopy of the lobster proteins, very large complex of 300 kilodaltons. And so we did a preparatory negative stain study, you know, and we got a very good reception with the grant proposal. But it's one of these tragic stories of alpha unfunded. You know, there was internationally excellent, but insufficient funds to allow us to go ahead with our one. Yeah, but anyway, try and do the best you can to embrace them all. And of course, each one of these developments helps us learn more about the limitations of what we do. I mean,
we should think about structural science, and you sort of start asking the next questions. With the rise of cryo-electron microscopy, what would be the role we see for crystallography in the future for structural biology? What are your thoughts on the integration of AI and machine learning in crystallography? What are the biggest benefits and potential pitfalls?
Well, of course, the big problem we have in protein crystallography is where things are too flexible to crystallize. And if we do crystallize them, that they're a particular conformation, which, you know, is perhaps not the range that exists in nature. So the the big complexes are things where cryo-EM has been particularly adept at providing structures, and they have, you know, that particular group happen to be ones that we really struggle with. But of course, the amount of material that you need for a cryo-EM, even if it might crystallize, you know, it's very, very small. It's a very economic with amount of material, which is very impressive as well. And with respect to the protein design and prediction, I mean, protein design in particular, you know, David Baker and his team always validated, you know, their designs with structures, and the protein fold side of the story, of course, they have to validate and actually see in the end whether their prediction is correct. But more than that, I mean, it was very interesting last week that the reactions to the Nobel Prize EuroXFEL in Hamburg were very quick, well, next day anyway, to I thought it was quite a bit of an unusual move for a facility to say David Baker was one of their users. I mean, I would have thought that was, to be blunt, confidential information until they've decided to publish. But it suggested to me that, you know, so therefore, what was the nature of the work that he was doing there? So is it structural dynamics? Is it time resolved stuff? So is he moving into design of different conformational states? You know, and he needs, nevertheless, to have an experimental foundation for that kind of work. But of course, that's also another area, to come back to your starter question. What should be our emphasis in the future? Well, it's obvious that multiple states and dynamics of structures is something that, you know, we can, you know, be in the most strong position possible. I mean, putting crystals as a state of matter are fabulously accommodating to both allowing us to determine structure, but also leaving flexibilities. You know, with 50% solvent, typically they can flop around into the solvent channels, and if anything is restricted, we can get a different space group and free up the movement of atoms. You know, so yeah, and then more natural philosophy. You know, there is this difference between precision and accuracy. And you know, if you want to be accurate, you need to apply 2 or more methods and see how well they agree. So you do your best to make each method's results for a given structure as precise as possible. And if you get the same results, well, you can say they're accurate. I mean, if you compare Acta F, had a wonderful set of papers in the 2010s, including from Kurt Wuthrick himself, and comparing NMR structures in solution of proteins with the crystal structures. And, you know, you can see where largely that they agree, and that's great. But you also saw particularly the strength of NMR, where the flexibility of, you know, the NRC terminus in particular, the electron density was washed out, but the NMR still gives some indication of where the structures were in the ensemble sense.
Is experimental phasing dead, with so many structures getting predictions with PLDT of 90, at least some of the chunks you can do molecular replacement with? Yeah, well, this has been a particularly fabulous success story for the fold prediction. I like very much Daniel Rigdon's recent paper. I think it was in Acta D, and he took about 1,000 protein crystal structures and data from the PDB and checked whether you could solve them with the fold prediction now versus SAD phasing before. And you know, there was only 5% that were left that
couldn't have starting phases from molecular replacement with the fold prediction. But I think, even there with 5%, if you're the, biochemist determined to get at some particular structure and mechanism, and the fold prediction isn't working out, that 5% is very important. And of course, the methods of tuning the wavelengths to enhance the signal of specific metals or ions for precisely locating those in the structure. There's lots of really important work there to be sure that what you put into the PDB with those identification and placement of metal atoms, are right. And the complementary method of X-ray fluorescence at the beamline tell you, what the nature of things is in the sample, but not exactly where they are, which is our domain, of course.
Yeah, I was going to say, to me, what really scares me is the possibility that certain methods would just be lost in progress. What does it mean for the community that something like, that requires a deeper understanding of crystallography, like experimental phasing, one day might get lost?
Well, I think that first of all, the Daniel Rigdon study suggests that they should not be lost. And certainly for locating and identifying properly metal atoms and ions in biological macromolecules is with us. There is alpha-fold 3, and that's being evaluated by the community. So there may be steps nibbling or biting into what we do as experimentalists with alpha-fold 3. We'll have to wait and see. But there is a very good coordination of synchrotron and X-ray laser and neutron facilities, with respect to, maybe in the future there would be, one or a few places rather than all that would do particular methods. I mean, the really terrific initiative at Diamond with the long wavelength beamline, the project led by Armin Wagner. I mean, that for low Z determination of atoms, potassium, and things like that. But it's a unique beamline in the world. So, but it's a facility that is available somewhere.
Let's say if you could change one fundamental limitation of crystallography, what would that be?
Very good question. I mean, the most fundamental is where we need a crystal. And so to somehow invent a method which allowed us to manipulate molecules into arrays, three-dimensional arrays. I mean, the control of atom placement by light, is something that physicists do, but that's of course individual atoms that are being manipulated by light, laser tweezers. So if we could somehow come up with a way of arranging, protein molecules to be precisely in a lattice, 3D lattice through the equivalent of laser tweezers, I mean, I think that the crystallization of biological macromolecules, it's moved much away from being purely art, and it really is that a tribute to the things like the international conferences on biological macromolecule crystallization. They've really charted a path towards that being a science and not an art. Yeah, they probably think I've fallen off the perch by suggesting laser tweezers to put proteins into a lattice. So
herding proteins, is it expected to be more difficult than herding cats?
Well, I've never herded cats, but it is a very vivid expression, which I think we can all conjure up what it means and the impossibility of doing it.
John, one more crystallographic question. Name one crystallographic routine or process that you would never do by hand.
Well, that's an easy one, really, because you know you'd never put a crystal in the X-ray beam inside the hutch with the shutter open. So
That's a good
and
answer.
I mean the early days. I mean, I met a fellow from Calcutta who worked at UMIST, University of Manchester Institute of Science and Technology, with Henry Lipson, and he used to align the camera to the X-ray tube head by looking down the collimator, and he said, "You see this deep dark brown stain on his head?" He said, "Well, that was the X-ray beam." But these things don't bear thinking about. We would never ever do that, right?
Oh wow. More generally, where do you think we would be without computers?
Well, we'd be pre-1948. Well, the first stored program computer officially is the one in Manchester, 1948. But of course, the Colossus 2 at Bletchley Park, for the Enigma, Alan Turing stuff for figuring out German military codes and messages. So if we think, what was it like pre-1944, 1945, then it would be continuing like it was then, and we'd be all using beavers' lips and strips to calculate as quickly as possible, 3 years for one structure, using these, I don't know if you've ever seen a box of beavers' lips and strips, but you do these, line up these strips of to do the equivalent of using a table of logarithms.
Well, in the region of crystallography, there were obviously human computers. They hired people.
Well, that was the role of you using the beaver's lips and strips. And I mean, the Babbage calculating machine was a precursor, if you like. And so, these things where you sort of turn a handle to do a simple calculation or addition, subtraction. I mean, the whole inflation of what we do. I mean, it used to be that, my PhD, I didn't complete the protein crystal structure I was working on. I mean, it took, 3 PhD students worth to do the one structure, and so on and so forth. And I was in Montreal at the IUCR Congress in 2017. I was having lunch with Zygmunt Derowenda. He and I had worked together at York. And he said, these days, John, it's not enough to solve one disease with a grant proposal. You've now got to propose that you're going to solve 5 diseases with one grant proposal. And it was part of this inflation of what we can do through all these things like computer tools and synchrotrons and what have you. Much more is expected of us.
So related to that, I know you've been a great proponent of open data, and the PDB, protein structures have had open coordinates for a long time. And that was obviously the basis of AlphaFold and Rosetta Fold and structure prediction. So now there's a move to make the raw data also open. Do you think that might lead to a similar breakthrough?
I think the emphasis and role of open raw data is not yet clear. So one thing I'm very keen on is that it ensures a bit again, the natural philosopher in me, natural philosophy being physics, that it allows the reader or reuser of a study to see exactly what was done and reproduce it or not. And so that's perceived by some as rather unexciting. And the more exciting things will be where you can measure data. It's fairly rare these days, but you can't solve it. And by sharing the raw data, then you actually might actually do that, and yet the measuring people can get credit for what they've measured, even though they can't take it to a full structure. But the open, I mean, PDB, fabulously successful because of its being able to be open, and it's, and I'm sure all of us have written very happily the letters of support for each 5 years renewals of the PDB's financial support, whether it's Wellcome Trust based in Europe for us, or NIH for the US based people using the PDB. But I mean, the Cambridge structure database used to be open because it was funded by public funds. Then Mrs. Thatcher came along, and she said, well, if it's valuable, people will pay for it, and they turned off the public funding. And so they survived as a charity and a force for good, but in a different way. And anyway, so I was asking myself the question, could crystal structure prediction for small molecules be solved if the CSD was fully open? And of course, we've also had an enthusiastic crystallography open database develop, and they're up to 500,000 structures, and CSD is at 1.2 million or something. But anyway, in my sort of browsing around, of course, I was reminded that the CSD in Cambridge they organise the crystal structure prediction challenges in the same format as the CASPs for the protein prediction, and they're up to number 7. So CSD isn't open. Its data are fair, findable, accessible, interoperable, reusable, and fair doesn't equal open. So I think actually the point I'm making here in sort of surveying the landscape more broadly, it is that there's a range of ways of doing things, and I suppose the bottom line, you could say, well, the PDB and design and prediction of protein folds has happened, whereas crystal structure prediction hasn't succeeded yet. So there is one way of saying, well, open PDB, has succeeded in ways that the chemical structure, crystal structure prediction hasn't. But I think that would be oversimplistic. So open data and raw data in particular, I think it's a fabulous development. That's obvious because of my enthusiasm and the time I commit to helping IUCR on it. But quite how it's going to work out will vary by field. MX is very enthusiastic. Vladek Minor, chair of the commission, is very much a prime mover in the area. And the chemical crystallographers the sample's very difficult, then it's obviously worth preserving the raw data. And the powder people are thinking about it. So there's a spectrum of views about the opportunity that large digital archives are giving us.
John, we are very curious to know, what is your favorite space group other than P212121?
Well, I always admire these chemical crystallographers who do this full 230 space groups thing. And but anyway, that sounds evasive. I mean, my PhD project involved one space group, C2221. And I suppose that being the first one I encountered, and I lived with it for so long, that would have to be my favorite.
Well, actually, I actually have a T-shirt with P212121 from the volleyball team when I was at Leiden University. But my favorite is P321.
Oh, all those 120-degree things stretch the mind.
Don't know if anybody else has any favorites.
PN3M.
Ah.
P21, PhD memories.
Okay.
A head banging one is I23 and its partner I213. because you get the problem of the 2-1 or not 2-1 hiding in the eye. So we got led the wrong way down that particular one at one stage. One of the concanavlinases was a headache for a while because of that.
Well, and the R32 and R3 are fun always also as well. I had a couple of those. Anyway. Okay, so the next, but yeah, let's go to the next theme. You've obviously been to a lot of congresses. So we were going to ask you, what were your favorite ECM and IUCR congresses?
Yeah, well, the one IUCR that I missed was 1978, and my wife and I got married instead. So that was the one I missed. And the first one was 1975. So, of course, I always vividly remember IUCR 1975. David Phillips introduced me to Jack Dunitz, and quite a character. If you've ever met, he's passed away now, but if you did ever meet him, you know, very interesting person, and certainly his papers, Jack Dunitz's papers, really very original and thoughtful. But I suppose my favorite congresses really, I mean, the ECM in Ravin in 2015, when I got awarded the Max Perutz Prize, you know, he's obviously very, very big in the mind. And the year before, at the ACA in Albuquerque, I was awarded the Patterson Prize. So these two premier prize awards from, you know, the likes of the ACA and the ECM, you know, they're just, yeah, never to be repeated, probably. Just fabulous memories from those.
So what is your view on carbon footprints? So obviously, thousands of people going to congresses far away is maybe not sustainable in the future.
Yeah. Well, this is really eating away as a problem at you know, how we work as a connected community of scientists. And I've not had a good track record in my carbon dioxide footprint. Obviously, I can do small contributions of, well, I cycle a lot, but they're minuscule compared to what I've cost the planet with my CO2. I think what's happening, early days, but I think what's happening is that, take IUCR, you know, it's a global entity, and it wants to share the Congress location every 3 years. So there is a sort of a principle of rotation of by continent of the Congress. And that gives a great opportunity for students, in particular young scientists in that particular continent, to attend a big conference. And so that's obviously CO2 more friendly, because, you know, you're imagining in that scenario a dominance of that continent's young scientists, senior scientists being the predominant attendees. But I think it's always going to need, you know, the global connectivity, and that means people flying in. And you can say, well, you know, do it hybrid. And I think hybrid is very good for region. So, you know, ECM, if it could be hybrid, ACA, if it could be hybrid, you know, you're within a restricted set of time zones. But once you do global Congress, then, I mean, like for Melbourne last year, I did wonder about attending by remote, but, you know, you'd have to attend the sessions overnight in UK, and that's not fair on you know, family, you know, so that's not going to work. So Research Data Alliance do an interesting thing, you know, along with International Science Council's Committee on Data, CODATA, they organize these data-driven events. And RDA repeat the session at 2 different times in the day. And so you can have participation by Zoom into the live session by, you know, different parts of the planet. And but of course that can lead to different, I mean, question time, you know, you can have a different suite of people in the audience globally, parts of the globe. And so you can have, in discussion, you can have quite different outcomes in the extreme case after a talk. But I think that's a particularly interesting one, that global organizations like IUCR should think about. But it would make the live event rather cumbersome, because you'd have to, and tough on the participants attending in person, because they'd have to repeat their talks twice in the day and so on. But that would certainly tackle the CO2 head on, whilst retaining the global role on the other.
My next question actually allows you to travel without having an impact on CO2 emissions, and moreover, it will allow you to go back in time, a sort of H.G. Wells type of question. So if you had a time machine, when would you like to travel back in time, and to see what and why?
Yeah, I'd love to be with my parents on the day that I got my end of school exam results and secured my University of York place to study physics. It was such a momentous thing for me, and it was obviously such a pleasing thing for my mother and father, that to be able to recreate that moment. So it's a very selfish wish to just recreate that fabulous moment.
Well, they must have obviously been very, very proud.
Yeah, I mean, my father was a policeman, my mother was a nurse. One other member in the extended family had gone to university. I was the only one to go and do science.
Right.
And I was the second one of the whole family to go to university. My cousin, who was older than me, he went to Glasgow University and ended up becoming a translator in Italy, and he still lives in Torino. And we talk every few months by WhatsApp video, which is nice. But yeah, the point being, not at all common in my family for you know, going to university. So that was a special thing, and science in particular was unheard of in my family.
Thank you, John.
In keeping with the science fantasy theme, I'm going to ask you to close your eyes and imagine yourself in the size of a water molecule inside a protein crystal. John, what do you see?
The strangest thing in the molecular world, and particularly in our protein world, in the crystal, you know, the solvent channels and all that, the dielectric constant, you go from no water molecules between 2 charges and 2 water to 1 water molecule, 2, 3, 4 water molecules. The force between those 2 charges, you know, goes from a value of relatively 1 to an 80th. So the dielectric constant of 80 is a phenomenal odd thing, and I think it makes the whole modeling of charge-charge interactions and water molecules in between. You know, you transition from the molecular level to the macroscopic one, and this dielectric constant varies in this 2 orders of magnitude way. So, and of course, the impact of that on the water molecule itself, you know, it's polarizable, and that's how it works. That's how it impacts on the electrostatic interaction between 2 charges, because it is so polarizable. So I think that's the most dramatic thing. It's not strictly seeing, of course, because I'm saying, you know, what is the force experienced by, you know, a positive and a negative charge as a function of number of water molecules in between them. So I'm cheating slightly by expressing it in terms of a force, but yeah, I think that's the most dramatic thing. It's very hard for modelers dealing with this. If you look at modeling papers, you know, I always look to see what are they doing with the dielectric constant.
Wonderful. We're reaching the end of the interview, and to conclude, we've got a few more general questions. The first one is about music. What music does John Helliwell listen to, and in what format? Streaming, CD?
You know, listening to music, I hate to say it, but my favorites list is a fairly regular set of ones that I listen to over and over again. And it's easy if I was ever invited onto Desert Island Discs, of course, I'd know them immediately. But the thing I've enjoyed in my semi-retirement is learning to play the classical guitar. And sometimes I can even make quite good music out of it. Not always, obviously.
So carrying on along these lines, so is there a non-scientific book or a piece of art that has inspired you in your scientific career or shaped the way you see and think about science?
I mean, the Dali representations are very eye-catching, and I remember going to a Dali exhibition in Rome off the Piazza del Popolo, and in there was this one where he does a rendering of a portion of a lady's head with an array of atoms, and that's incredibly striking painting, and I don't know if it actually inspired anything in particular, but I certainly felt awestruck when I saw it. I think in terms of books, novels, I mean the C.P. Snow Two Cultures fellow is a very interesting set of novels, and there's one in particular, The Search, which is close to our field, and sort of progresses as a research scientist undertaking structure determination, you know, I can't remember exactly, 70 years, 80 years ago. I remember reading Michael Rossman's, so it was sort of a review of his scientific life type of thing. And lo and behold, he said the same thing. He thought that C.P. Snow's The Search was really an inspiring novel, you know, imagining very much our sort of life and Michael's sort of life, and how it works out and so on.
Thank you, John.
John, we are heading to the end. So my last question is, what is something about you that might surprise people who know you professionally?
When I retired, you know, when I had to give up squash, I used to play a lot of squash, and I got all these problems with my joints, and obviously I couldn't carry on with it. So I joined a gym, and of course you see people doing things in the gym a lot of the time way out of one's own scope, but occasionally you see people do something, you think, well, maybe I could do that. And so there was one such moment as I watched a fellow doing these press-ups, and I thought, bloody, no, I better not swear. I thought, blooming heck, you know, I ought to be able to do a few press-ups. So I said to the trainer guy, how do I go about it? He said, well, you won't believe me, but you'll have to just start on your knees and be very, very patient, and you'll be able to do a few. And I said, well, yeah, but when will I be able to do a full press up? He said, well, you'll just know that you might like to try and attempt it. and it won't work out, and then you just keep persevering, and you do these every day, and so on. And then in the end, I managed, to do a full press up, and I'm up to 47. I did 47. I did this morning before breakfast, and I feel so much better for it, and I don't have any of those squash playing joint aches and pains that I used to have either. So that's.
You used to do rowing as well, the ergometer?
Yes, well, Oxford is very good for that sort of opportunity, and you can eat like a horse and never put on an ounce of fat, and you develop this triangular shape, from broad shoulders to narrow waist, and but anyway, you also meet various folks I did rowing 8s, and for the mainly for the graduate boat, and you meet these characters from the Rhodes scholars from America. Bill Clinton was a Rhodes scholar, and so on, and you meet these characters, and they were ever so confident. I mean, the public school boys that you met in the rowing were confident. I was from a state school, so rather sort of whatever the word should be, anyway, not so confident. And then these Rhodes scholars, they were unbelievably confident characters, and they were very interesting to study and learn from.
Yeah, I think I remember from Twitter some ergometer.
Oh, yes. Well, at the gym, my favorite machine is the rowing machine, and I did quite well for a while, and was getting very fit and doing these fast times over long distances, and I had one of these rush of blood moments on Twitter where you say something like that. And actually John White at ESRF, John Wright at ESRF said, oh, well, there is a social media thing where you can log your time for your age group, and I think I was 127th in the world or something for my age on that. I haven't entered any other data since, so I have no idea where I am now. I seem to be getting slower, but I suppose that's inevitable, really. Anyway, so we got to these questions about my gym trips. So I've got to haul you back and think about this. I mean, I really do think that the topical reviews of gathering the fabulous structures together on a theme has got great potential for the future. But so far, I've not been able to persuade anybody else besides me and my co-authors to write any of them. But hopefully the penny will drop in the wider community, and I think Acta F, is really a fabulous place for bringing these themes together. And of course, the most recent one, glucose 6-phosphate dehydrogenase, Stefania Hanau, I said, how about we write this next one? And she said, well, okay. But then, of course, we found that about a quarter, a third of them were cryo-EM ones. Because this enzyme, can get quite big, and of course, cryo-EM was the method. And so Tom Burnley at the CCP EM, based at the UK Rutherford lab there, he helped me how to assess the cryo-EM structures, and the maps, the electrostatic potential maps. They were very impressive, I must say. Anyway, so there we had the G6PDH topical review. They are getting, I noticed that the earlier ones that I did it, steadily accumulating citations, which they should, of course. And that's
yeah, I have to admit I haven't looked at that. I have to check that. And
yeah, I mean, they're not fast burners. I mean, they're slow burners, whatever the phrase should be, but they are accumulating citations, as they should do.
There was a general one on NMR that accrued a lot of citations, but that's already maybe 5 years ago or so.
Let me ask all of you a question. So are you planning your Calgary footprint for what Acta F will be doing within the IUCR journals efforts at Calgary for the 2026 Congress?
Oh, I don't look so far ahead.
We've got a few ideas.
I'm hoping to be there. I got to secure the funds yet, but and of course you provoked all these thoughtful worries now about CO2 footprints. And it would be easier to be from UK to zoom in to Calgary. I suppose it's what, 7-hour time difference. So that's easier than Melbourne by a little bit, not a lot. Well, thanks ever so much, guys, and yeah.
Thank you, John.
Was very pleased to be invited, I must say.
Thanks,
I
John.
hope my answers were not too boring.